Chapter 10 is going to be essentially a continuation of Chapter 9. But we're going to be talking about a topic called stoichiometry. It sounds complicated. It's actually really not that complicated. You use stoichiometry all the time. When I'm making cookies at home, if my recipe calls for 2 cups of flour and 1 cup of sugar, that 2-to-1 ratio is the stoichiometry of my cookie recipe. And I'll be talking more about chocolate chip cookies later on. The key thing about stoichiometry is maintaining a balance between chemical compounds. We want to make sure we have the correct ratio or balance between the various substances. The good thing about Chapter 10, when all said and done, it's basically just one kind of problem you'll need to know how to do. It uses essentially the same unit plan with just some subtle variations. So I think you'll find Chapter 10 is going to be a bit of a breath of fresh air here. We've had Chapter 9 was a bit more complicated. Chapter 10, usually the hardest part of it will be learning how to spell stoichiometry, and I'm actually not going to ask you to do that anyway. So other than that, it's a pretty straightforward chapter. Why don't we go ahead and get started?
Stoichiometry is sort of a scary sounding term. It's a big, complicated word, but it's actually rather straightforward in practice. It's simply relating the reactants and products in a chemical reaction, essentially the amounts of each of those things that are present in a chemical equation. For example, let's take a look at the reaction to make ammonia from nitrogen and hydrogen. You can see that there's a 1-to-3 ratio of nitrogen to hydrogen, and there's a 1-to-2 ratio between nitrogen and ammonia, and a 2-to-3 ratio between ammonia and hydrogen. That is the stoichiometry of the reaction. It simply relates the coefficients in the balanced equation. We could, for example, double the amount of nitrogen in the reaction, and all we have to do then is double the hydrogen. As long as we keep that ratio the same, we're maintaining that 3-to-1 stoichiometry. We would have to do the same thing, of course, for the ammonia. As I've said in the past, chemical reactions or chemical equations are very much like recipes. In the same way you can double or triple a recipe, you can do the same thing with the balanced chemical equation. We could make the nitrogen 3.5 times larger, and we would simply do the same thing with the hydrogen and the same thing with the ammonia. Now, you can write conversions between the various substances in a chemical reaction to represent that stoichiometry. For example, we can write the conversion 3 moles of H2 to 1 mole of N2. That is a conversion that relates those two substances. We can write a conversion between the ammonia and the nitrogen. We can write a third one between the hydrogen and the ammonia. You can take any 2 substances in that balanced equation and you can make what's known as a mole-to-mole conversion. That's the one new kind of conversion that we learn in Chapter 10. Back in Chapter 9, we spent a lot of time with gram-to-mole conversions, and we're going to use those again in Chapter 10, but add to that this new thing called a mole-to-mole conversion. Now, how many of these mole-to-mole conversions will you need to memorize for Chapter 10? The answer is none, because they all come out of a balanced chemical equation. Any stoichiometry problem that I give you to work on is going to start with a balanced chemical equation, so that will be provided for you. The coefficients in front of each substance in the chemical equation will allow you to come up with these mole-to-mole ratios. Like any other conversion, of course, these can also be flipped upside down, depending on which way you're going. If you're trying to go from nitrogen to hydrogen, you would want to use it this way. If you're going from hydrogen to nitrogen, you'd want to simply flip it upside down. And the same is true with both of the other conversions or mole-to-mole conversions for this particular equation. Let's take a look now and see how we can use these mole-to-mole conversions to carry out some stoichiometry calculations. How many moles of ammonia could we make from 13.4 moles of nitrogen? Chemists use stoichiometry all of the time. If we're going to make a chemical and we need a certain amount, we need to know how much to start with to get that amount. So in this case, our starting point would be the 13.4 moles of nitrogen. We want to get from moles of nitrogen to moles of ammonia, so we would want to use this conversion in the middle here that relates those two. And of course, we would want the moles of ammonia to be on the top so that the moles of nitrogen would cancel, and we end up with 26.8 moles of ammonia. Now, suppose we wanted to know how many moles of hydrogen we would need to react with that 13.4 moles of nitrogen. We can't make this ammonia unless we have enough nitrogen and hydrogen. We could begin once again with our 13.4 moles of nitrogen, but this time we're trying to get to moles of hydrogen, so we'll use this ratio. And again, we'll put the moles of hydrogen on the top because that's what we're trying to find out. And we get 40.2 moles of hydrogen. Now, there's another way we could have figured this out. We've already determined that 13.4 moles of nitrogen is equal to 26 moles of ammonia. So we could have started the problem with the 26.8 moles of ammonia. It's like saying if A equals B and B equals C, A must equal C. We could go from ammonia to hydrogen by using this third conversion. And if we do that, we're going to get the same 40.2 moles of hydrogen. So stoichiometry is just simply a way of relating the amounts of substances in a chemical reaction. So you can calculate how much of each substance you need. You can figure out how much of the product you're going to get. Cooking, as I've said before, involves stoichiometry. Cooking and chemistry are very similar. A balanced chemical equation and a recipe are essentially the same thing. A balanced chemical equation tells you what you're going to combine, what you're going to get, and how much of each substance there will be. A recipe does the same thing when you're cooking. This is my chocolate chip cookie recipe. In a normal semester, for the final exam, I bake about 500 of these cookies and I bring them all into the final exam for the students. It's sad that this semester we won't be able to do that simply because we're doing all of our class online. But this recipe is essentially like a balanced chemical equation. It tells us the ratio between flour and baking soda, or brown sugar and white sugar. Now, over the years, I have found that sometimes it's easier to weigh my ingredients rather than measure the volume. We talked about that earlier in chapter 9 when we discussed counting by weighing. So when I bake the cookies, I commonly weigh things because it's quicker and more accurate. We can make ratios or conversions out of any two ingredients in this recipe, just like we did with any two ingredients in our chemical equation we looked at a moment ago. So 2.5 cups of flour to every 1 cup of Crisco. That's one possible conversion. 5 dozen cookies for every 2 eggs. That is another conversion. 1 cup of brown sugar to 1/2 cup of white sugar. Again, there's a lot of different conversions that you could make between the various ingredients or the product of this particular recipe. We can do the same kind of calculations here we did with the ammonia. How many cookies can you make from 10 eggs? Our starting point logically then would be 10 eggs. We know that we get 5 dozen cookies for every 2 eggs, so our eggs will cancel out, and we end up with 25 dozen cookies. That's a lot of cookies. We could also calculate how much sugar would be needed. We can't make the 25 dozen cookies with just the eggs. We need the right amount of all the other ingredients. So we could now calculate how much sugar would be needed to make that same 25 dozen cookies. So we begin with our 25 dozen cookies, and we know that it takes half a cup of sugar to make 5 dozen cookies, and that means we're going to need 2.5 cups of sugar. We can go through that same calculation for every ingredient in the recipe. All this talking about cookies is making me hungry. Why don't we go put stoichiometry to some practical use and make some cookies?
Hi everyone. I think it's time we take a little break from chemistry and do some cooking. We've been talking about the fact that stoichiometry applies not only to chemistry but also to recipes. So I've shared my chocolate chip cookie recipe with you. Let's go ahead and make some chocolate chip cookies. So you've already seen the recipe. So we'll start out with some of our dry ingredients here. As you saw in my recipe, I have found that weighing some of the ingredients is easier than actually measuring out volumes. It's more accurate. So according to my recipe, I need 360 grams of flour. So let's start out with that. Now there's over 200. We're getting close. Just about there. And there we go. So there's our flour. We need a teaspoon of salt and a teaspoon of baking soda. So let's get our salt and baking soda here. Make sure we level that off. There's our baking soda. Now we'll get some salt. So that's our dry ingredients. We're going to go ahead and set that aside here. Now we need to get some of the moister ingredients. So we'll start out with the Crisco. Crisco being really greasy and sticky, I found it's a whole lot easier to weigh it than it is to measure it out in a cup. So we need about 180, a little more than 180 grams of Crisco. Now that's 140, we're just about there. All right, just a few more grams. All right, there's our Crisco. We need 220 grams of brown sugar, so let's tare our balance again like we would do in the laboratory. We'll add that 220 grams of brown sugar. There's about 150. There's 200. And there's our 220. We need 100 grams of regular sugar. Let's go ahead and weigh that out. There's 80, 90. There's our 100 grams of sugar. We need a couple of eggs. I'll try not to embarrass myself and not crack the eggs very well here. I'm not actually a chef, I'm really a chemist. That wasn't too bad. Not exactly chopped material, but not terrible. And finally, we need a teaspoon of vanilla. So we've got our vanilla extract here. I always use real vanilla. I don't like that artificial stuff. I like the real vanilla here. So we'll want a teaspoon of that. And that's the main ingredients that we need. So everything is in now except the chocolate chips, and I like to add some nuts as well. So I'm going to go ahead and get this stuff all mixed up, and then we'll reconvene here in a minute, and we'll start getting those cookies ready on the cookie sheet. All right, let's go ahead and get these ingredients mixed together. So first I'll mix up the shortening and the sugars and eggs and vanilla, get that nice and creamy. A mixer can be handy, but I've always done this by hand. We'll stir up our salt and baking soda and flour so it's at least fairly uniform. It won't be homogeneous, of course, as you well know. We'll go ahead and add now the dry ingredients. Get that all mixed together and make our dough. So we'll work that flour in here. All right, let's go ahead and add our chocolate chips. I, of course, can't resist at least stealing a couple off the top. Love chocolate chips. And it's optional, but I am a big fan of walnuts. So I'm going to go ahead and put in a cup of walnuts. I like those nutty flavored cookies, plus it makes more cookies if you put some nuts in there. It tends to expand the dough here. So I'm going to mix this for a couple of minutes, and then I'll show you what it looks like, and we'll get some cookies on our cookie sheet. All right, I've got the dough all mixed together. You can see it here. It's got just about exactly the consistency I like to have. My oven's just heated up. I have a convection oven, so as the recipe said, for a convection oven, it takes about 9 minutes to make a batch. I have these really large air-baked cookie sheets. I bought these years ago because if we were on campus, I would be baking about 500 cookies to bring to the final exam. So my apologies that you're going to miss out on that this semester. But these cookie sheets, I can bake about 30 at a time, so it goes pretty quickly. When I'm making hundreds of cookies, the more I can bake on a sheet, the better. So I'm going to go ahead and put 30 cookies out onto this cookie sheet. And I just sort of eyeball the size here. And yes, I've washed my hands in case you're worried. Plus the fact my wife and I have not been going anywhere during COVID, so chances of me having coronavirus are just about zero. So I'm going to go ahead and get 30 cookies put on that sheet, and we'll start the baking process. All right, the first batch is ready to go. I've got my 30 cookies on the cookie sheet. The oven's heated up to 375, so let's go ahead and put these in. Set our timer for 9 minutes. All right, 9 minutes, we should have cookies. While that's going on, I'm going to prepare another sheet, and in a few minutes, we'll see what the first batch looks like. Well, it looks like the first batch is ready to come out, so let's see what we've got here. Oh, those look pretty good. We'll let those cool for a couple of minutes. Go ahead and put the second batch in, then we'll try one. All right, 9 more minutes, we'll have the next batch. Well, there's our timer. Looks like the second batch of cookies should be about done. I think we'll give them just a few more seconds here. While we're doing that, I think we can try out one of the first batch. That is a good cookie. All right, let's see if this batch is done here. They look just perfect. So maybe by next year, guys, we'll be back on campus again. I'll be able to once again make cookies for my students for the final. But if nothing else, you can try this recipe at home yourselves.
All right, now that we've satisfied our hunger, or at least I have, with those fresh chocolate chip cookies, let's do some more stoichiometry problems using our cookie example. When you buy things like flour or sugar at the grocery store, it doesn't come in cups. Even though our recipe is in cups, it comes by the pound. So if we want to figure out how many cookies we could make from 5 pounds of flour, our problem is that the recipe is not in pounds, it's in cups. So we would simply have to come up with a conversion that related pounds and cups. And fortunately, I have already done that. I've measured this in the past. So I calculated that there are about 3 cups of flour in every pound. So we can change our pounds of flour into cups. Now we have the correct unit for our recipe. From there, we can then figure out how many cookies we get for a certain amount of flour, and that comes out to be 30 dozen cookies. All I've really done here is just expanded the problem a little bit. Since we didn't start with cups, we simply have to get into cups. If we had started with ounces, we'd have had to gone to pounds and then to cups. Whatever we do, we have to end up with the units that are in the recipe, and in that case it happens to be cups. All right, how many pounds of flour would you need to combine with 4 pounds of sugar? Sugar is normally sold in 4-pound bags, so how much flour should we buy if we wanted to use up that 4 pounds of sugar? We would start, of course, with pounds of sugar, but again, pounds is not the unit of our recipe, it's cups of sugar. We'll then need to change pounds into cups, and this is another thing that I have measured and found that there's about 2 1/4 cups of sugar in a pound. Once we get to cups of sugar, we can use our recipe to get to cups of flour. And of course, once we've gotten to cups of flour, we can use this conversion from the previous problem, and that will get us back to pounds of flour. And it turns out we would need 15 pounds of flour to go with that 4-pound bag of sugar. So that's about 3 5-pound bags of flour for a 4-pound bag of sugar. Although my students sometimes complain that all of my food-related examples make them hungry in class, especially if they've skipped breakfast, I find food examples to be useful because the chemical examples that we do actually work the same way as the food examples, and where chemical problems tend to scare students and make it more difficult for them to understand the concepts, if you can realize that a simple recipe calculation is essentially the same thing, it should make it a little less scary. So let's take a look now at some chemical stoichiometry problems. Let's consider this acid-base reaction between phosphoric acid and sodium hydroxide. How many grams of sodium hydroxide would you need to react with 53.2 grams of phosphoric acid? Well, we're running into the same problem we did a minute ago in our cookie example. The phosphoric acid and the sodium hydroxide in the equation are not in grams, they're in moles. What this tells us is you need 3 moles of sodium hydroxide for every 1 mole of phosphoric acid. There's nothing in this equation about grams. But that's no problem. All we have to do is change our grams of the substance into moles, and then we can plug it into the equation. The same way that we changed the cups of sugar or flour, the pounds of sugar or flour into cups so that we could plug them into our recipe. Our starting point then is going to be grams of phosphoric acid because that's the thing we know. In order to plug it into the equation, of course, we'll need to change it into moles. That's what we learned about in Chapter 9. We learned that you could determine the molar mass of a compound and then use that molar mass to go back and forth between grams and moles. Once we get to moles of phosphoric acid, now we can make the jump to moles of sodium hydroxide because we know there's a 3-to-1 ratio between those. And of course, from moles of sodium hydroxide back to grams, that's just another gram to mole conversion that we can use the molar mass of sodium hydroxide to figure out, and now we have our answer. This unit plan, grams to moles to moles to grams, that is essentially the only unit plan you need for all of Chapter 10. Every problem in the chapter is basically this kind of problem. Occasionally I'll add something a little extra. I might start you with pounds, or I might end you with kilograms, but that's relatively simple. This is the core of every stoichiometry problem in the chapter. So we'll start with our 53.2 grams of phosphoric acid, and we'll want to convert that into moles. So if we calculate the molar mass, it comes out to be 98 grams. From there, we can go from moles of phosphoric acid to moles of sodium hydroxide, and from the balanced equation, we can see that's a 3-to-1 ratio. And then finally, we want to get to grams of sodium hydroxide, and the molar mass of NaOH is 40 grams, which gives us 65.1 grams of sodium hydroxide. This is essentially as complicated as Chapter 10 is. I give you an initial amount of a substance, and I ask you to come up with a final amount. You're going to use this same basic unit plan to do that conversion problem. As we did with the cookie recipe, you can choose any two substances in the reaction to relate. So this time, let's relate the phosphoric acid to the water. We'll want to start then with our grams of phosphoric acid and change it to moles once again, but this time we're going to go to moles of water and finally to grams of water. So instead of sodium hydroxide, this time it's the water we're interested in. Once again, we'll start with our grams of phosphoric acid, convert that into moles. Then we will go to moles of water per mole of phosphoric acid, and finally we'll change the moles of water into grams using its molar mass, and we end up with 29.3 grams of water. We could do another calculation if we wanted with the sodium phosphate. You can pick any two things out of the reaction. Let's take a look at a different chemical reaction now, aluminum fluoride and calcium in a single displacement reaction. So we have 13.7 grams of calcium, and we would like to know how many grams of aluminum we can make. Our unit plan, of course, will be, as always, grams to moles to moles to grams. And since the calcium is the known quantity, that's what we'll start with. We'll begin by converting our grams of calcium into moles using the molar mass of calcium. We can then use the ratio from the equation, which is 3-to-2. So we have 2 moles of aluminum for every 3 moles of calcium. And then we can convert the moles of aluminum into grams, and we get 6.15 grams of aluminum. We could also calculate how many grams of calcium are required to react with 0.45 pounds of aluminum fluoride. Ooh, I threw a pound in here. That's going to just make a small change in our unit plan. Our plan will still be the basic grams to moles to moles to grams. We simply have a pound at the beginning. So this takes us way back to Chapter 1. We simply want to begin by changing pounds to grams, and then we'll do the usual stoichiometry calculation. The first thing we'll want to do then is change our pounds of aluminum fluoride into grams. We can then convert that to moles using the molar mass of the compound. From the stoichiometry of the reaction, we know that we get 3 moles of calcium to every 2 moles of aluminum fluoride. And then finally, we can change the moles of calcium into grams, and that comes out to be 146 grams of calcium. In all of the problems that we've done so far, whether it's been with chocolate chip cookies or chemical reactions, we've been making one very critical assumption, and that is that we always have enough of all of the other substances in the reaction or the recipe that we're dealing with. For example, when we calculated that you could make 20 dozen cookies from 10 cups of flour, that's only possible if we have enough eggs, chocolate chips, vanilla, so on and so forth. We're assuming that we have enough of all those other ingredients to make all the cookies. Same thing is true in a chemical reaction. In each of these problems we've done where we've calculated how much of something we need or how much we can get, It's always assuming that all of the other ingredients are present in sufficient quantity. Remember that a stoichiometry problem can only look at two things at a time. You might have 4 or 6 chemicals in a chemical equation, but you can only use stoichiometry to look at 2 of those. So the concept of limiting reagents suggests that one of the chemicals in the chemical reaction is probably going to run out first. The odds of you having exactly matching amounts of all the chemicals in the laboratory is highly unlikely. That's no more likely than in my kitchen. When I was baking cookies earlier, I had exactly matching amounts of flour and sugar and eggs and vanilla and so on and so forth. Clearly, one of those ingredients in my kitchen was going to run out first, and when it did, I'm done making cookies. Once one ingredient's gone, my recipe can no longer be carried out. So how do we figure out what the limiting reagent is in a particular reaction? Let's go back again and take a look at a cookie example. We'll be using that same recipe we did earlier. Let's suppose that in my kitchen I found I had 10 cups of flour and 6 eggs and plenty of all the other ingredients, so more than enough of everything else. So I was wondering how many cookies I could make with this much flour and this many eggs. When you do a limiting reagent problem, it's actually no more complicated than any other stoichiometry problem. You just have to do it more than one time. For the first part of our problem, we're going to look at the flour. Let's figure out how many cookies we could make from 10 cups of flour. We can convert the cups of flour into cookies and we come out with 20 dozen cookies. Now, that's assuming that we have enough of everything else. But let's take a look at the eggs and see how many cookies we could make from these eggs. Well, from 6 eggs, if we convert that to cookies, it comes out to be only 15 dozen cookies. What that tells us is, as soon as we reach 15 dozen cookies, we've run out of eggs. Even though we still have enough flour to keep going, there aren't enough eggs, and so we're done making cookies at 15 dozen. So the answer to the question is, how many cookies can you make? It's however many the limiting reagent will allow you to make. So in this particular case, eggs would be the limiting reagent, or in this case, the limiting ingredient in our recipe. The flour is known as an excess reagent. In this case, all the other ingredients would be excess reagents. If we had more than enough of everything else, in a chemical reaction, you only have one limiting reagent, but everything else in the reaction would be an excess reagent. Let's take a look at a chemical example. We'll bring back an equation that we looked at a few minutes ago. But this time, I'm going to ask you how many grams of aluminum you could get if you had 13.7 grams of calcium and 16.4 grams of aluminum fluoride. One of those two is clearly going to run out first. So let's figure out which one it will be. First, we'll calculate using the calcium. So based on that calculation, this is one we did earlier, we came up with 6.15 grams of aluminum could be made from 13.7 grams of calcium. We now need to do the same type of calculation, but this time we'll begin with our grams of aluminum fluoride. So from aluminum fluoride, we'll take it to moles, then we can go to moles of aluminum and to grams of aluminum, and this time we find we only get 5.27 grams of aluminum. So the aluminum fluoride gave us less aluminum than we could get from the calcium, just like the eggs gave us fewer cookies than the flour did, and that means that our limiting reagent is the aluminum fluoride. Whichever reactant produces the smallest amount of the product, that is your limiting reagent. All right, the last topic in Chapter 10 has to do with determining what's called the percent yield of a reaction. It's basically just a measure of how efficient a chemical reaction is. The higher the percent yield, the better the reaction has run. And of course, not surprisingly, 100% yield is the best you can do. So if you get every single molecule or every single gram of material that it's possible to get, then you have 100% yield. This type of thing is very important in chemical companies. I worked for a number of years in the chemical industry before I got into teaching. And when you're making millions of pounds a year of various chemicals, even a 1% increase in 1,000,000 pounds of material, that's 10,000 pounds of extra product you have to sell. So chemists and chemical engineers spend a lot of time trying to get the percent yield in their reactions to be as high as it can possibly be. The first thing we need to know is the theoretical yield. The theoretical yield is what we've been calculating using stoichiometry. It's the maximum amount of the material that you can produce in your reaction. So every time we do a stoichiometry calculation, we're figuring out what's the best we could do. Now you also need to know the actual yield. The actual yield is essentially what you got when you ran the chemical reaction. And of course, the only way you can get the actual yield is to actually do it. You have to go into the lab or into the manufacturing plant, carry out the reaction, and simply weigh the amount of material that you ended up with. On a quiz or exam, I would always provide you with the actual yield. We can then calculate the percent yield by comparing the two. So the percent yield, as we said before, is simply a measure of how efficient a chemical reaction is. And we calculate that by looking at the actual yield and the theoretical yield. So the actual yield is what we got in the experiment. The theoretical yield is the best we could do, which we've calculated from stoichiometry, and then we simply multiply that by 100. So the best you can possibly get from a percent yield is 100%. If you get more than 100%, then that means you've done something wrong, because that would violate the law of conservation of mass. You can't get more out of a process than you put into the process. All right, let's work through a sample problem here. So in this reaction of aluminum and fluorine combining to form aluminum fluoride, we're starting out with 13.7 grams of fluorine. We have an excess of aluminum. That means we have more than enough aluminum to react with all of the fluorine. And I'm telling you that we got 17.6 grams of aluminum fluoride, which is our product. So that 17.6 grams, that is the actual yield. The theoretical yield, you're going to have to calculate using stoichiometry. So we're going to use the same unit plan that we always use for stoichiometry problems, and grams to moles to moles to grams. So we always start out with the material we're given. We know how much fluorine we have, and we're trying to find out the amount of aluminum fluoride. Because grams cannot relate directly to grams in a chemical equation, since chemical equations are based on moles. It's 2 moles of aluminum, 3 moles of fluorine, and 2 moles of aluminum fluoride. So for substances to communicate in a chemical reactions, they have to speak mole language. So the first thing we do is take our grams of fluorine and change it to moles. Then the moles of fluorine will be converted to moles of aluminum fluoride using the coefficients in the balanced equation, and then using the molar mass of aluminum fluoride, we can get back to grams. So we'll start out with our 13.7 grams of fluorine. Then using the molar mass of fluorine, which is 38 grams per mole, we change the grams to moles of fluorine. Then, looking at the balanced equation, we have 2 moles of aluminum fluoride produced for every 3 moles of fluorine. And then finally, we want to convert that back to grams. So adding up the molar mass of aluminum fluoride, we have 1 aluminum and 3 fluorines. That would be 84 grams. And that gives us the amount of aluminum fluoride we could expect to get from this reaction. So we would expect to get 20.2 grams of aluminum fluoride, and that would be the theoretical yield. That's the best we could possibly do. So if we want to calculate the percent yield, we need to compare the theoretical yield with the actual yield that was given in the problem. So as we said before, the percent yield is simply obtained by dividing the actual yield by the theoretical yield, multiplying that by 100. So we plug in our two numbers, multiply it by 100, and we get an 87% yield. Is that a good yield? It depends. In some reactions, 87% would be excellent. In other reactions, that would be terrible. It depends on the inherent efficiency. Some chemical reactions, if you got 50%, that would be phenomenal. And other reactions, if you got less than 90%, it would be terrible. So there's really no way to judge that. All right, let's see if we can put everything together that we've talked about in Chapter 10. So we want to calculate the theoretical yield, we want to figure out what the limiting reagent of a reaction is, and finally figure out the percent yield of a reaction. So this time we're going to be looking at the reaction of hexane and oxygen to produce carbon dioxide and water, so a basic combustion reaction. This time I'm going to give you amounts of both of the reactants, both the hexane and the oxygen. So 113.5 grams of hexane is combined with 351.2 grams of oxygen. One of those is going to run out first, and we want to figure out which one that is. Which one is the limiting reagent? The simplest way to do that is to simply start with each of these in a separate problem. So the first thing we'll do is figure out from 113.5 grams of hexane, how many grams of carbon dioxide could we get? Then we'll do a second calculation where we'll begin with our 351.2 grams of oxygen and figure out, in that case, how many grams of carbon dioxide we could get. Whichever one of those produces the smaller amount, that will be the limiting reagent. And that smaller amount will be our theoretical yield. And of course, to get the percent yield, you need the actual yield, which is also provided here. This is what we actually got. So your job is to figure out which of these two is going to give us the least amount of carbon dioxide, and that will be our theoretical yield. So let's start out with the hexane. We have 113.5 grams of hexane. We'll convert that to grams using the molar mass of hexane. And then using the balanced equation, we have 12 moles of CO2 produced for every 2 moles of hexane. And then finally, we want to convert that back to grams of CO2. Molar mass of CO2 is 44. And that tells us that we will get 348.4 grams of carbon dioxide in this reaction. That's the best we could do. However, we need to find out how much we can get from the oxygen. So this time we'll do a second calculation, but we'll begin with the grams of oxygen. Then using the molar mass of O2, we'll change that to moles of oxygen. Again, looking at the balanced chemical equation, we get 12 moles of CO2 for every 19 moles of O2, so that's our coefficients here. And then once again, we'll want to change moles of carbon dioxide into grams. And this time we get 305 grams of CO2. So it looks like the oxygen gave us a smaller amount of CO2 than the hexane did. And that means that our limiting reagent is the O2. Whichever substance produces the smaller amount of material, that is our limiting reagent. So our theoretical yield is however much you get from the limiting reagent, which would be our 300.5 grams. So the hexane in this particular case would be an excess reagent. We had enough hexane to get all the way to 348.4 grams, so we're going to end up with some leftover hexane at the end. As soon as we reach 305 grams of CO2, we've run out of oxygen, and so even though there's hexane left, there's really nothing we can do with it. So finally then, to get our percent yield, as we've talked about before, we divide the actual by the theoretical yield. So the 288.3 grams of actual yield divided by the 305 grams of theoretical yield, and we get a 94.5% yield.
Well, that wraps up Chapter 10 and our discussion of stoichiometry. As I said, it's pretty straightforward. Essentially, there's only one unit plan, grams to moles to moles to grams. I might add a pound on one side, a ton on the other, but basically it's just that single unit plan. So unlike Chapter 1 and 8, where you had to come up with a different plan for every problem, in Chapter 10 it's all the same one. Whether you're calculating percent yield or limiting reagent or whatever, it's the same calculation. And of course, the important thing you should have learned is that stoichiometry applies to cooking. Making chocolate chip cookies obviously involves a lot of stoichiometry. Unfortunately, since I won't be seeing you guys in person for the final, I won't be able to bring those cookies in that I do normally every semester. So hopefully a video version of that will have to suffice for this semester. So that's essentially everything in Chapter 10. We're getting pretty far into the semester now. We've only got 3 chapters left. That's 13, 14, and 15. So our second exam will be coming up now after Chapter 10. Just 3 chapters left to go, and then we'll have our third midterm exam, and then the final, and all will be done. So let's go ahead and start preparing for that exam, and then next week we'll be moving into Chapter 13.